Okay, so where we started last time, we were talking about Chapter 1, and Chapter 1 is basically the first part of calculus. In general, in this course, we're going to be looking at two different parts of calculus. We're going to look at differentiation and integration. Differentiation is when essentially we're going to be looking at the slope of a line and the slope of curves. Why we're interested in the slope of a line or slope of curves is, as we're going to see, it tells us how quickly something's changing. Like if you were plotting the pay rate you get from a company over time, how it's been changing, that might be some interest to you. Okay, that would be the slope of some curve or the slope of some line. If you were plotting a car's distance over time, the slope of that line would tell you how fast the car is going, and things like that. Integration, which is going to be the second half of the course, is concerned with finding the area under some curve. Similar to finding, say, the area of a square or the area of a circle, if we have a more complicated curve, we'd like to find the area under it, which can be useful in a number of applications we'll look at. Then we're going to treat that with integration, which will be the second part of the course. Okay? So this is just a repeat slide from last time. We were looking at what a line is, okay, because we're going to use lines, the slopes of lines, to determine the slopes of curves at points. So the first thing that we talked about last time was that a line is an equation or a function that can be written in the form of y equals mx plus b, where m is the slope or the rate of change of the y values, and b is the y-intercept. Now, for this slide, like I said last time, don't worry about what those mean at the moment. Just memorize what they are. The b term, or the constant term on the end, is the intercept term. The m over here is the slope. An example of that is y equals 3x minus 4. In this case, minus 4 is the y-intercept, and 3 is the slope. Okay, so that's something we looked at last time, and we went over some examples of other lines and some things that are not lines. Okay, we also looked at this slide last time, and these are some graphs of lines with positive slope. Okay, so let's say we're plotting on the x-axis, we're plotting time, and on the y-axis over here is, say, your particular pay rate at the company you're working at over time. Now, you expect, as time goes on, you would expect the line to go up somewhat. You wouldn't expect it to go down. So when there's a positive slope, like in this equation over here, 3 is a positive number. So that means the slope is positive. That's my slope, that's my m over here. And for all of those, the slope is positive, means we go from lower left to upper right. You can see in this case over here, the 2 is positive. It means we're going to go from lower left to upper right. It does not matter what the intercept is. Here's another example where we have the line y equals 2x. 2 is a positive number. That's the coefficient in front of the x. Again, we have a straight line going from lower left to upper right. And over here, again, we have y equals 2x plus 1. Here, the y-intercept is a positive number. It doesn't make a difference. We're going from a lower left to an upper right. Conversely, if the slope is a negative number, again, it does not matter what the y-intercept is, then the line is going to go from the upper left to the lower right. Okay, so it's going down. As time goes on, say on the x-axis, the y value is going down. So if this were the pay rate example again, as time goes on, it would mean that the amount that they pay you weekly or whatever is decreasing. Okay, that's that scenario. Right? So in this case also, and in this case also. It does not matter what the y-intercept is. The y-intercept will change where the line starts, in some sense, but it doesn't change whether the line is going up or down. It just changes where the thing is starting at. Okay? So those are the lines we looked at last time, and this is the example we stopped at. Okay, so we're going to look at this example in a little bit more detail, and we're going to look at properties and lines. So we have a salesperson's weekly pay depends on volume of sales. If she sells X units of whatever good she's selling, then her pay is given by the equation y is equal to 5x plus 60. Okay, so this is an equation that tells her how much she's earning, and the amount is in dollars. So give an interpretation of the slope and the y-intercept of the straight line. Okay, so let's take a look at this. So let me just write it down here real quick and switch over. Okay. All right, can everyone see that okay? Yeah, okay. So this over here is how much she earns. Okay? Y is the amount that she's earning. That's how much she's going to get paid. And X over here is the number of items she sells. Okay? So can anyone tell me how much does she earn if she sells zero units? She earns $60, okay? So $60 is kind of like your starting point. The y-intercept over here, 60 is the y-intercept, okay? $60 over here, this is the y-intercept, right? That means when the x value is 0, that's going to be where the line is. That's going to be the y value. In the case of earnings, when x is 0, it means that this is how much she's getting paid if she sells nothing at all. Okay, so this is her base pay. Right? Value in x equals 0. Okay, can everyone see that? I'm going to try and get the lighting a little better. And when I post the video also, YouTube has a nice feature where it enhances the lighting. But okay, so now the 5 is the slope. Okay, so this 60 over here, this is the y-intercept, right? Or it's the value of the line when x equals 0. And it's also given on the line by the point 0, 60, right? When x is 0, y is 60. We're going to look at that in a second. Now, this over here, the 5, okay, this is going to be the slope of the line, right? If we're talking strictly about a line. If we're talking about an application, it's going to be a rate. In this case, the units are going to be dollars per item sold. Right? So the units of this over here, I'm sorry the lighting's, I'll get that fixed for next time, but this 5 over here, it means she gets $5 for every item she sells. So if x is 1, ignoring the base pay, if x is 1, she's getting $5. If x is 2, she's going to get another $5 on top of that. If x is 3, she's going to get another $5 on that. It's going to be $15. If x is 4, she's going to get $20 on top of the base pay. If x is 8, she's going to get $40 on top of the base pay, and so forth. Okay? So an interpretation of what's going on here is, from the problem, is she has a base pay of $60, which is the y-intercept, right? It's the value when x is 0. And we have the slope over here, which is the rate that the y value is changing. So it's the slope. So the slope is essentially gives you how fast something is changing. Now in a straight line, it's always going to be a constant number. In this case, it's 5. When we go on to curves, the curve, we're not going to have a constant number. The rate's going to change over time. A common example where that comes up is a car accelerator, right? If you do a plot of distance versus time, and we're going to see this later on, the rate that the car is gaining distance is increasing. Not just the distance of the car increasing, but the rate that it's gaining distance is increasing. That's what acceleration is, okay? So we're going to talk a little bit about that too, but for now, does anyone have any questions on this example that we're doing here? 5 over here is your slope, and it's the rate that she gets paid at. and she has a base pay of $60, right? So what you want to know is the intercept over here is the value of the line when y is 0. In this case, is what she earns if she sells nothing. She's guaranteed a salary of 60. And the slope is how quickly you're accumulating dollars per sale. In this case, you're accumulating $5 per sale. Okay? All right. So now that we have that on, let's look at a plot of this line now that we have an idea. And what they're doing is they're choosing to look at the point. What happens if she sells 80 units? Can someone tell me how much she's going to earn if she sells 80 units? $140? Okay. $460. Because 8 times 5 is 40. 8 times 5 is 40 plus 60 is 460. Okay? So what she ends up earning is, remember, just to review, the x-coordinate goes on the left, the y-coordinate goes on the right. So if she sells 80 units, she's going to earn $460. Let me just do that real quick over here, just a quick review on that. So we have the equation y is equal to 5x plus 60. Okay? And we ask what happens if she sells 80 units. That means x represents the number of units sold, so x is 80. So we say y is equal to 5 times 80 plus 60. Right? Because we're saying she sells 80 units. So 8 times 5 is 40. So 80 times 5 is 400. Plus 60 is 460. Okay? So that gives us the point on the line when x is equal to 80. We know that her earnings for those sales give her $460. Okay? So let's go back to the example. Stop me if you have a question. Okay, so we have this over here, and this is exactly what we were just talking about. The 60 represents her base pay, and the 5 is how quickly she's earning money per sale. For each additional sale, she's gaining $5. So the slope of the line is the rate, how quickly she's earning money, and the 60 is representing the base pay. If the slope were negative, then she'd be paying money out. So a lot of times in applications, we talk about earnings or gains in mathematical applications, and if we want to represent a loss, we'll just represent that as a negative earning. Makes things a little easier. Okay, we're going to go over some properties of lines now, and I'm going to refer back to the other example a little bit. The first property is nice to know. It'll help you out. It's basically just a reinterpretation of what the slope is, and it helps us when we're trying to plot a line, okay? So the idea here is, and I'm going to illustrate it, if the slope of the line is m units, in the last example was 5 units, what does that mean? It means that if she sells one more unit, she gets $5 more dollars in the last example. So if we were to go out 2 units, we would end up going 10. Okay? So it means, geometrically, it means that if we're trying to plot a line and we have one point and we know the slope, to get the next point, we can just add 1 to the x and m units to the y. Okay, so let's go back to the previous example, and let's look at this line over here. Okay, so 8 and 6. Okay, so we have this line over here, and we're gonna plot it. Now, just as a review, when you're plotting a line, to plot any line, all you need is 2 points, or a point and a slope. Okay, so right here, we have this line, and we have a point at 80 and 460, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go by 10, so it's going to be 10, 20, all the way up to 80. And I'm going to go by 50s up this axis, so I'm going to go 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. So 450 is over here, 460 is going to be, so this point is going to be over here somewhere. And we want to plot another line on the axis. Well, of course, we have the y-intercept, so let's end up pointing 3, which is when x is 0, the y-coordinate is, well, let me write this over here. This is going to be 80, 460, right? Now, we automatically have another point. The y-intercept tells us when we've sold nothing, the value is going to be 60. So this is 50, this is 100, 60 is somewhere in here. So this is going to be 0, 60. Okay? All right. Now, suppose we wanted to, suppose that we're starting at the point 0, 60, and we add, and we want to go forward by 1 unit. Well, if we went forward by 1 unit, okay, that means that we're saying, well, if we make the 0 into a 1, we go forward 1 unit, how many units do we go up in the y direction? So if you sell 1 more, how much more do you earn by increasing your earnings by 1 unit? 5. So we go from 60 to what? 65, right? So if I were going to go forward 1 unit, I would go 10, 20, 30, 40, 50, 60. Oh, if I go to forward 1 unit from the, let's see, the numbers are too close together, so let me redraw that. Okay. All right, so this is the point, say 80, 460, right, that we have on the line. So let's make this point over here so I can draw it more easily. Now, forget the thing with the 0, that's fine, but I'm just doing this for illustration purposes. Now, suppose we go forward, so the x-axis over here is at 81. That means we have a point on the line up over here, where this point is going to be 81, 465. And we can go forward 1 unit again. Excuse my drawing, it's hard to fit these on the page. But if we go forward again by 1 unit, so this is going to be, say, 82, then we go up another 1, and we have the point which is going to be 82, can someone tell me what's going to be? 470. I'm off the page. How about now? Is that better? Okay. 80, 470. And I can go to 83. I'm going to have 475. So another point in the line is going to be 83, 475. 84, 480. So basically what the slope means, if I go 1 unit in the x direction, what happens if I went 2 units in the x direction? Then how much would I increase by? If I went directly from 80 to 82, I'm not going to go up by 5 units. How many am I going to go up by? 10, right? Okay. So I hope that wasn't confusing. If not, come see me and I'll go over that again. My drawings are not the best. All right. So let's see over here. So let's go back over here. And that's what this first thing is saying, is the slope of the line is how quickly the line's going up, okay? It's not enough to plot the line because you need to start from somewhere. But if you have the slope in a point, you can figure out another point by going 1 over to the right and m up straight where m is the slope. Same thing if we're negative, except, of course, you'd be going down because m is a negative number. And remember, when you have zero slope, means you have a flat straight line that doesn't change. Okay, we looked at that last time, and that's going to come up again. So zero slope is really important in calculus because it means something is not changing. Okay, so very important. Very, very important. The next property is very important also. It's a formula you should have memorized. And you may already have it memorized from previous courses, and that's the slope of the line. If you're given 2 points, the slope is the change in the y-coordinates divided by the change in the x-coordinates. Okay? So if we go to our previous example, all right, so make sure you have this formula written down, all right? Make sure you know this. You're going to need it all, you're going to need this frequently. So it's the change in the y-coordinates divided by the change in the x-coordinates. Okay? All right. So we have this example over here. Okay. So we have this example over here of the line, and it doesn't matter what 2 points I pick, as long as I'm consistent with which is y1 and which is y2, which is x1 and x2. x1, if this is my x1, this has to be my y1. If I use this is my x2, this has to be my y2. Okay, so it doesn't matter which point is point 1, which point is point 2, as long as x1 and y1 and x2 and x2 go together. So I can calculate my slope m, which better come to 5, as y1, which is 460, minus y2, which is 465, divided by x1, which is 80, minus x2, which is 81. Can you see it now? Okay. Minus x2, which is 81. And again, I'll work on the lighting for next time. And this is just going to be equal to 460 minus 465 is what? Negative 5. And 80 minus 81 is going to be negative 1. And a negative divided by a negative is a positive, and you see we wind up with the slope back as 5, which is what we expect, right? If you didn't want to deal with the negatives, you could just do 465 minus 460 divided by 81 minus 80. It doesn't matter which you make x1 and which you make x2, as long as your x1 and your y1 stay together and your x2 and your y2 go together. Okay? If you have more questions on that, you'll get some practice on the homework and so forth. Okay, so let's go back over here. The next property is another way to write a line. So these are all properties that are important. They're going to come up. And that's property 3. We're going to call that slope property 3. The equation of a line can be obtained if we know the slope and 1 point on the line. So this is going to be one of the most common formulas we use throughout this class. All right, we're going to use it more than the form of the line, y equals mx plus b. That's useful for graphing, but this particular form is just going to come up a lot. All right, it's completely equivalent to the other form, except for the types of problems we'll have here, it's easier to write down the answer using this formula. All right, you can use y equals mx plus b. You can figure out the slope. This is called the point slope form, because you cannot read the y-intercept directly from the equation. This is useful if you know the slope and a point, because if you know the slope and a point, you can write an equation directly down. All right? And let me do an example of that. So if we go back to if we go back to our example over here, we know the slope is 5, and we're going to use the point 80, 460. Okay? So we're going to use the point which is 80, 460. And we know that the slope is equal to 5. Okay? Now, we know that the point slope form is going to be equal to y minus y1 is equal to the slope times x minus x1. Okay? Now, my point is going to be x1. It's going to be my first coordinate of the point. And y1 is going to be this. And it can be any point on the line. It doesn't matter. It's going to be x1, y1. That's an x over here. So this is going to be y. Well, y1 is 460, so it's going to be y minus 460 is equal to the slope, which is 5, times x. Well, x1 is 80, so it's going to be minus 80. Okay? Now, if I simplify this and I solve for y, you're going to see it's going to be the equation we started with, which is, I think, was y equals 5x plus 60. All right? So we just solve for y. So y minus 460 is equal to 5x minus 400. Now I'm going to add 460 to both sides. And I'm going to have y. These are going to cancel to give me 0. So I have y is equal to 5x. And positive 460 and a negative 400 gives me 60. And I wind up with the original line. So this is in the form y equals mx plus b over here. And this up here is written in our new form. So in calculus, it's going to be a lot quicker to write them down in this form. Sometimes you might have a homework or problem or something that might ask you to write it in the slope-intercept form. All right? And this is the point-slope form because you use a point, x1, y1, and a slope. This is the slope-intercept form because you have the slope, which is 5, and the intercept, which is 60. They're equivalent. You just have different information looking at one versus the other. All right? Slope property 4, distinct lines of the same slope are parallel. Conversely, two lines are parallel, they have the same slope. All right? So parallel lines are lines that never intersect. So if you have two different lines with the same slope, they never meet each other. Okay? And that's always true when they have the same slope unless they're the exact same line, just written differently. Like, for instance, what do we mean by that? Well, this is a line written one way. This is the same line written another way. They are not parallel lines, they're the same one. Okay? If I made this a 61, then they would be parallel because they would be different lines, but they have the same slope, which is 5. Okay? Two lines are perpendicular when they never intersect. They make right angles. A way to find this, if you have a line and you want to find a line perpendicular to it, we're going to use the property that the products of the slope are going to be -1. And we're going to do an example with that in just a second. So first, here's an example they do in the book. Find the slope and the y-intercept of this line. This is a nice straightforward example, and it works on some algebra skills. What we're going to do is we're going to break up this fraction over here into two parts. Instead of writing x plus 1 divided by 3, we can always rewrite it like this, and that's using the property from fractions. If you have a common denominator, in this case a 3 and a 3, you can just add the numerators to keep the same denominator. So if we add x plus 1, we get x plus 1, keep the denominator. Okay? So just to review from fractions, sometimes when you throw an x in there, people forget what it is. And of course, this is the same as 1/3 x plus 1/3. So we wind up with a line over here where the y-intercept is 1/3 and the slope is 1. Okay? So that's just an example of taking something like this up here and writing in slope-intercept form. Okay. So this is another example of property number 1. We did an example like this. We're going to see an example from the book now. So we're going to do an example using property 1 now. Okay, we did an example before. 1 unit increase in the x direction means m units up in the x direction. 2 units means you're going up m twice, so 2m, okay? So we're going to do another example just like we did before of that, just one from the book. And sketch the graph of a line passing through the point -1, 1 with slope 1/2. Okay? So first let's look at what they do, and then we'll do it again on paper to clear up any confusion. We use slope property 1. We start with the point -1, 1. Now, if we go 1 unit forward in the x direction, what point are we at? So we're starting at the point, we're starting with the x value -1. So if I go 1 forward to the right from -1, where am I at? 0. And if I go 1 forward in the x direction, how far do I have to go up in the y direction? How far? 0.5 is correct. Whoever said that. 0.5 is correct. The slope is 1/2. So this means if I go forward once in the x direction, I go up half a step in the y direction. That's what the slope means. So if I go forward 1 in the x direction, this -1 is going to be -1 plus 1 is 0. And what is the y value going to be? What is it going to be? 1.5 is correct. 1.5 is correct because if we go 1 forward in the x direction, then this becomes 0. And if we go 1 forward in the x direction, the slope of 1/2 means for every unit we go forward in x, we have to go 1 up in the y. I mean, a half up in the y because the slope is a half. So if we go 1 forward in the x, -1 plus 1 is 0. That means we have to add 1/2 to this 1, or 0.5, so we get 1.5. Okay? So that's what they're going to do here. So, I'm sorry, they do something to make the numbers work out a little bit nicer. But what you said is completely correct. They go 2 forward in the x direction. So if I go 2 forward in the x direction, then what do I have? 1. If I start at -1, which is over here, I go forward 1, I end up at 0. If I go forward again, I end up at 1. But now I have to go up a half and another half. So I start at so I'm starting at the point over here, which is 1. I go up a half, which is going to be 1.5, and I go up another half, and I get to 2. So I end up at the point 1, 2. Let's look at that real quick. So I have the point -1, 1, and I have slope a half. Okay? So I have the point, and this is exactly like the example we did before. It's just a different example in the book. If I have the point, -1, 1, and I have m equals 1/2, what is that telling me? Well, it says, like one person says, if I increase this by 1, I get to 0. And that means I have to increase the y by a half, or 0.5. So this becomes 1.5. I can go forward again. If I increase the 0, if I add another 1, what do I get? 1. How much do I have to add to the 1.5? What do I get? 2. And I get the point. So I have 3 points on the line now. And what they do is they go directly from -1, 1 to 1, 2. they add, to negative 1, they add 2, so I end up with 1. And since I added 2 here, I have to add 0.5 twice. So 0.5, 1 plus 0.5 is 1.5, plus another 0.5 gives me 2. Okay? So that's exactly what they're doing here. They're starting at this point, negative 1, 1. They're adding 2 to the x-coordinate, which means I have to add a half and then another half to the y-coordinate, or 1. And I go from the point negative 1 comma 1 to 1 comma 2, which is up here. Okay? All right. All right. Okay. Let's look at another example. We're going to find the equation of the line that passes through the points negative 1/2, 0, and 1 comma 2. All right. Now, what we're gonna do for this now, we're going to use property number 2 and property number 3. All right. Property number 2 is just the slope formula. We did an example like this. We're going to use the formula that the change in the y-coordinates over the change in the x-coordinates gives me the slope. Property number 3 is the point slope form equation of the line. So once I know the slope in a point, I can plug it into that formula, and I have the equation of the line in point slope form. And then I'm just going to simplify it so it's in slope intercept form. Okay? So I have the points over here, negative 1/2, 0. And I also have the point 1 comma 2. All right? All right. So that's a little hard to read. Okay, this is the point negative 1/2, 0, and that's the point 1 comma 2. All right? So M is going to be equal to 2 minus, what is this? Minus negative 1/2, right, divided by what? What is it going to be? So my y-coordinate minus my other, did I make a mistake? Yes, I did. It's going to be equal to 2 minus 0. This y-coordinate minus this y-coordinate divided by this x-coordinate, which is going to be 1, minus what? Minus 1/2? Negative 1/2. All right? Now, this is going to be equal to 2. And this is going to be equal to what is 1 minus a negative 1/2, right? Which is going to be what? Which is going to be 1.5 or 3/2, right? And this is just going to be equal to 4/3. Okay? So then what we're going to have is, so again, what we did here is, first of all, given 2 points, the first thing we need to do is find the slope. So I'm going to make this y1. So I'm going to do y1, which is 2, minus y2, which is 0. So it's 2 minus 0, divided by x1, which is 1, minus a negative 1/2, which is going to be 2 divided by 1.5, or 4/3. And now this is my slope. Now what I can do is I can pick either one of these points, it doesn't matter, and I can use property 3. So I'm going to use the fact over here that it's property 3 that y minus y1 is equal to m times x minus x1. Now I know that the slope is 4/3, so I'm going to pick the point 1 comma 2. So y is 2, so this is going to be y minus 2, right? I can use either point. I'm going to use the point 1 comma 2. So I'm going to have y minus 2 is equal to, my slope I said was 4/3 times x minus what? So my y coordinate is 2, what's my x coordinate? Well, it's going to be 1, so it's going to be minus 1. Okay? So now what I'm going to do is I'm going to, now this is the point slope form of the line. I'm going to write this now in the slope intercept form. So I'm going to have y minus 2 is equal to 4/3 x minus 4/3. And I'm going to add 2 to both sides. So what I did there is just distributed the 4/3 to the x and the minus 1. So I get 4/3 x minus 4/3. I'm going to add 2 to both sides. So I'm going to have y is going to be equal to 4/3 x minus 4/3 plus 2. But I can also write 2 as 6/3 because 6 divided by 3 is 2. And that should be a 3. Right, okay. So then what I have here is the denominators are both 3, so 6 minus 4 is 2. So I have y is equal to 4/3 x plus 2/3. Okay? Now you're going to see it again, just with the PowerPoint. I don't remember which point they use. Yeah? You could use either one. Does not matter. Yeah, unless there's a mistake in the calculation somewhere, of course. But otherwise, it should be the same. So we're going to do the same thing here. They did the same thing we did, and they get a slope of 4/3, right? And then what they do is they use property 3 like we did, which is the point slope form of the line. And they're just going to pick one of the points. They picked the same point we did. And they just plug 2 in for y1 and 1 in for x1. And then they just simplify, distribute, add 2 to both sides, and they're done. Okay? So any questions on what we just did here? All right. Okay, so now we're going to go over the last property of the line. Find an equation of the line that passes through the point 2, 0, and it's perpendicular to the line 2x. Now what we'll have over here, we have a point, we just need to know the slope. Right? Find an equation of the line that passes through the point. So we have a point on this line. We don't know the slope. But we know it's perpendicular to the line y equals 2x. So we know 2 times the slope of this line will equal -1. And that's what they're doing here. So m is going to equal to -1/2. I think it's a little bit confusing with all that verbiage, so let's take a quick look through here, and then I'll do it on paper. So we start with, we have a point on the line, and we're going to use property 3 once we know the slope. So we just need to find the slope and use property 3. To find the slope, though, we're going to use a previous property, which is property number 5. If we take two perpendicular lines and we multiply their slopes together, we get -1. Okay? So let's go back to this question. So if we take the slope of this line, which is 2, and we multiply it by the slope of the line we're looking for, it's going to equal -1. Okay? So let's look over here. And we have the line y equals 2x. So we have the line y is equal to 2x. Now I'm going to call the slope of this line, I'll just call it m1, and the slope we're looking for is m2. So we know m1 has a slope of 2. Now we're looking for this other line, and we'll call that m2. This is the slope of the line, the perpendicular line that we're looking for. We don't know what it is. But what do we know? We know the slope of this line, which is m1, which is 2, times the slope of the perpendicular line that we're looking for is equal to -1. That's from property 5. So if we take m1 times m2, we get -1. Perpendicular lines, you multiply their slopes together, you get -1. So 2 times m2 gives me -1. If I divide both sides by 2, I know that the slope of this line I'm looking for is going to be -1/2 or -0.5. All right? So now what I have the slope of this line, and the question gives me a point on the line. So I can come back here, and then it's pretty simple. All right? This is what we just did. We found that we're looking for a line perpendicular to this line that passes through this point. We just found on the dock camera that the slope of this line is equal to -0.5, and we know we have a point which is 2, 0. So we can use property 3 using the point 2, 0 and a slope of -0.5. So the x coordinate is going to be 2, the y coordinate is going to be 0. The slope is -0.5. If we want to write it in slope-intercept form, we distribute the -0.5, and we wind up with this as our final answer. Okay. Slope as a rate of change. Now, lines have a constant rate of change. So the point of this question here, or maybe you guys can answer it for me. Compute the rate of change of the function over the given intervals. So we want to write this, to figure out what the slope is, we're going to write this in y-intercept form. And I already forgot what it was. Y equals 2x plus 27. So we have y equals 2x plus 27. I'm sorry, y plus 2x equals 27, right? Is this in the form y equals ax plus b, mx plus b? How can I get it in the form y equals mx plus b? Subtract 2x from both sides? I think I heard? Okay. So if we subtract 2x over here, and we subtract 2x over here, then 2x minus 2x is what? 0. So we wind up with the y over here is going to be equal to 27 minus 2x, or equivalently negative 2x plus 27. If you do 27 minus 2x, or just do negative 2x plus 27, it doesn't matter. So what is the slope of this? Is this in the form y equals mx plus b? What is the slope? Negative 2. All right. Let's go back to the question now. Okay, so what is the rate of change? Forget where it says 0 to 1 and 0 to 0.5. What is the rate of change or the slope of this line? If you ignore the interval, just what we talked about before. What is another way to talk about slope? We talked about at the beginning of class. Starts with an R. First word is rate. Rate of what? Rate of change. Slope is rate of change. What is the slope of this line? If we go back to here. What is the slope of this line? Negative 2. Yes? Can you say that again? No, the rate tells you how quickly the y values are changing. The rate of a line is constant. That's what this problem is going to be about. Okay? The rate of a line is constant. All right? So if you plot something and it's a straight line, that means if it's going up, it's increasing, it's not accelerating. All right? You have a constant rate of change. You're getting $5 for that. The lady in the first example gets an additional $5 for each box she sells. She doesn't get $5 for the first box, and for the second box she sells, she gets $5 plus a bonus. That would be an acceleration. Because she's just not getting $5 for each box, so if you plotted it, the graph could look something like a curve. Because she starts out slow, now she's speeding up. Every item she sells, she's getting benefits on top of the amount she earns just for selling that. That's an acceleration. The rate of change for a line, this number over here, it doesn't change for a line. And it doesn't increase, it just tells you how fast y is increasing. Does that answer your question? Okay. So what is the rate of change for this line? What is the slope of this line? -2, right? So if we go back over here, what is the rate of change of this line over here? We just said it. What if we restrict it to the intervals -1, 0 to 1, and 0 to 1/2? Does it matter? Raise your hand if you think it'll change. Raise your hand if you think it'll stay the same. Okay, let's look. Okay? All right. So let's go over here. And this is the equation of the line. The y-intercept is going to be 27. And our slope is going at 2x. So let's look at this line over here. We know that when x is 0, y is 27. That's what the intercept over says. When x is 0, y is 27. So we're going to go 5, 10, 15, 20, 25, 30. 27 is going to be about over here. Now we can, if we go forward in the x direction to 1, then we're just going to decrease by how many? So if we go forward 1 in the x direction, how many are we going down? What's my rate of change? -2. So this slope tells me if I start at a point in the line, go forward 1 in the x direction, how many do I go down in the y direction? 2. The slope tells me if I go 1 forward in the x direction, if it's a positive number, this number right here is going to tell me how many units I changed in the y direction. If we're a positive 2, I would go over 1 up 2. Since it's a -2, I'm going to go over 1 down 2. Right? That's what that -2 tells me. So if I start at the point, which is going to be over here, which is 0, 27, because my y-intercept is 27, all right, then that tells me if I go 1 in the x direction, so now my x-coordinate is what? If I start at 0 and I go forward 1, what is my x-coordinate? Yeah, it's gonna go down 2. So I'm gonna go from 27 to 25. So this is gonna be the point 1, 25. So I have these 2 points over here, 0, 27, and 1, 25. The slope is -2, so if I increase 1 in the x direction, the slope is -2, so if I increase 1 in the x direction, going from 0 to 1, since the slope is -2, increasing 1 in the x direction says I decrease by 2 in the y direction. The slope is -2, so go from 27 to 25. And I'm going to wind up with a point over here, which is going to be, 1, 25. Maybe not the most accurate drawn line in the world, but now the question is saying here is 0 and here's a half, and here is, say, the value 1. Ignore these points now. I'm just okay. So what is the slope of this line between 0 and a half? -2. The slope of a line does not change. Do you see the line going up or down at all? It's just a nice, straight, smooth line, okay? For every 1 unit you go here, for every 1 unit you go this direction, it goes 2 down here. If you go another 1 unit over here, it's going to go 2 more down here. If you go another 1 unit down here, it's going to go 2 down here. Does it ever do something like, if you go here, it all of a sudden drops 10? Will the line do that? No. All right. So what this question is saying, and I don't know if I'm communicating the idea well or not, it doesn't matter if you look on the interval from 0 to 1 or 0.5. The slope of a line does not change. It's constant. You can look on 0 to infinity. You can look at 0 to negative infinity. You can look at 0 to 1, 0 to half, 0 to 4, 0 to an eighth. You can look at -1/8 to 4. It doesn't matter. A slope of a line does not change. A slope of a curve in the next section, they change. Okay? So they did exactly what we did here. Subtract 2 from both sides. We have this equation over here. And the slope of a line is constant. It doesn't change. And on both intervals, the slope is -2. All right. So the slope of a curve at a point. So what we're going to do here. All right. Let's see. Okay. Slope of a curve at a point. So what we're going to do at this is we're going to get an intuitive idea about how to talk about how fast a curve is changing, right? For instance, if we take a car that's accelerating and we plot distance over time, it's not going to be a straight time, because every second that the car accelerates, the amount it gains is going up. The example of the lady selling boxes or items or said goods or whatever. If she gets $5 for each new box she sells, that's a constant rate. If she sells, if for every new box she sells, she gets, say, a 20% increase on that sale, the amount of money she gets, then her rate's accelerating because she's getting the base amount, plus she's getting 20% off the a 20% increase for her next sale, a 20% increase for next sale. She's not getting $5 more. She's making additional money, new additional money with each sale. So she starts out with the 60 no matter what. She gets $5 for the first sale. Say she gets $6 for the second sale, plus the original 5. Then say she gets $7 extra on the third sale, instead of 5, the constant rate, and then she gets 8, 9, 10, so forth. You plot that, and it's not going to be a straight line. You're going to see something with a steep incline. It's going to, not an incline, it's going to shoot up straight like this. And that's what we're going to see in this case. Now, where does this whole idea of calculus come from? Well, it comes from physics. Mathematicians trying to solve physics problems, and Isaac Newton is the mathematician / physicist, one of the people that worked on calculus. So calculus has close connections with physics, and it also has close connections with areas like finance and things like that. But it starts out with physics, and straight lines are not very interesting. Everyone knew how to compute it at the time. They wanted to compute if they were say dropping a rock off a building, right? It goes faster as it gets closer to the ground, so it accelerates. They'd like to know, okay, how quickly is it accelerating? Or various other phenomena. So they wanted to ask questions like that, and they knew intuitively what they wanted to do. They could, draw lines to kind of guess what they wanted, but mathematically, not sure of the answer. Well, the circle, you can compute, and last time I taught this course, I did this. I don't know if I'll do it. Maybe I'll post a video or something on it. The idea of a tangent line on a circle It's a circle, it's a line that intersects the circle in exactly one point, right? So if I can draw what's going on there, and the nice thing about the circle is why it's the motivating problem, is you don't need any calculus to do it. You just need to know what the equation of a circle is, and you need to know how to compute slopes of perpendicular lines. So I'm not going to work that out, but just to go over the idea, or what they were thinking, is if you have a circle here, and you wanted to know, all right, this relation here does have a constant rate of change, this graph, because it's not a straight line. It's not a straight line, it's not a constant rate of change. And say this is 0, and say this is x equals 1. Okay? Over here. So they wanted to know, okay, well, how fast is the curve changing at x equals 1? So they said, well, if I can draw a line through this point, since both this curve and this line share this point, and they both are changing the same rate at this point, if I can find the equation for the line that intersects the circle exactly this point, and I know how to find the rate of change for a line, it's just m, and when you have the form y equals mx plus b, then I can know how quickly the curve is changing at that point, for that time. And you can do that without calculus, because if you know what this point is, and you know that this is the point 0, 0, you have 2 points in a line, and you have this point, and you just find the equation for the line perpendicular that has that point. So I'm not going to work through that specifically, but you don't need calculus to do that. We need calculus in general because most any application and anything you'd want to look at, it generally doesn't tend to look like a circle. And circle might be one of the only examples I can think of. Well, I can think of others where you'd have some nice property like this. So in general, we need something better, but we have this intuitive idea of what we want. If we could draw a line that passes through the point on the curve that we want, and we knew that, say, it only hit this point, it didn't hit any others, then the slope of this line would be the slope of the curve at that point. So what we're going to do is we're going to estimate slopes of curves by drawing lines. They're going to be called tangent lines. Okay, so the physicists knew what they wanted, but they didn't really know how to calculate specifically what they were looking for. They could verbally describe it, they couldn't mathematically compute it. All right, and that's what they're doing here. They're saying if we want to find how quickly the curve is changing at this point, we're just going to draw a line that hits the circle once at that point, and you can kind of see that at exact point, the slope in this curve has the same exact rate of change. Okay? So maybe it feels a little fishy right now, but we're going to get lots of practice with this idea. Okay, so definition. What do we got here? This is just an intuitive idea of what's going on. All right? What we're doing here is we're just trying to get an intuitive idea of what's going on. Most lines, if you take any random curve and you take a point, the line intuitively that you're looking for doesn't necessarily intersect the curve in one point. So the method that they use for circle fails. And let me show you what I mean. Okay? So if we have this over here, say, if we have this circle, it's nice. But say we have, in no math right now, just an intuitive idea of what we're going on. This is kind of what the physicists were doing. Right, so if we have a curve that looks something like this, right? It's not a constant rate of change. Ideally, we would like a formula that tells you how fast the curve is changing at a certain time, right? Suppose we wanted to know, say this is x equals 1 over here. Say this is the point, say this is 0, x is 1. So at this point, how fast is the curve changing? Well, if you had to draw a line that would have the same rate of change, intuitively, and a lot of this starts from intuition, you would want something maybe like this line. Okay? Right, this line over here. Right? Because kind of this line, they both share this point. Say this is 5 over here, and say this is the point 1 comma 5. Both the curve and this line both intersect with line 1 comma 5, and they both kind of have the same rate of change there. They're both dropping as quickly as the other one. Okay? So if we go down a little bit on this curve, we approximately have the same change in y for this line. You see how they're kind of both at this point, and they're both kind of going down at the same speed. Later on, they tend to depart because this guy keeps going down, this guy dips below and shoots back up. So this guy has the negative rate of change. He's decelerating. Then over here, this line starts turning around. It starts accelerating. Then rate of change is positive now, right? But at least locally around this point, this line kind of has the same behavior as this curve. Okay? So it's just an intuitive idea. All right? And it doesn't, mathematically, we can't define this idea like the circle because, look, it hits in 2 points, but this point doesn't tell us anything about the slope of the curve because look how different they are. The line is dipping down over here and then shooting back up. So this point is completely useless to us. But this point over here, at least locally, this line is going down at a certain rate. And at least locally, this line over here is kind of doing the same thing. So if we kind of estimated a line over here from the slope of that line, we kind of have an idea about how fast this curve is changing. So just intuition. Anyone have any questions on that? No math there, just a bit of intuition about what's going on with these curves. This is kind of like the physicists when they're trying to run their experiments. They kind of know what they want off the graph, they just don't know how to get it off the graph. Okay? All right. So here's an example, and if this is our tangent line to the curve, then the change in x is, if we want to know how fast the curve, estimate how fast the curve is going at this point, well, we find the slope of this line. And you can see if we go 1 unit in the x direction, so our change in x is 1, we go up 1 unit in the y direction. So what's the change in y divided by the change in x? 1. Because you can see, we don't know, if this is the tangent line to the curve, then the slope of the curve at this point, well, we know that it's the slope of a line is the change in y over the change in x. Well, the change in x is 1. If we go 1 forward in x, we go 1 forward in y. So that tells us that the slope is 1. Okay? Slope of a curve is a rate of change. All right? The slope of a curve tells us how fast the curve is changing at a certain point. If you're looking at a car that's accelerating, a lot of times they look at acceleration from 0 to 60. And you looked at distance versus time, you wouldn't see a straight line because every unit of time that goes by, the car is gaining more and more ground, right? So the amount of distance that it gains with each second that goes by is increasing. So, all right. So let's look at this example over here. Okay. Let's look at this example over here. Refer to the figure below and decide whether the following statements about depth per capita are correct or not. Justify your answers. The depth per capita rose at a faster rate in 1980 than in 2000. Okay, so this is just intuitive. We're just trying to, so we go to the graph, we go to 1980, and it seems to be going up pretty steep over here. If we look at 2000, the tangent line over there looks kind of flat. Okay? So if you look at 1970, you can see if we try to draw just estimated tangent line over there, that's a very steep curve. It looks like what we're looking at is the values on the y-axis here are going up pretty steeply. We're over here, remember, a flat line means a zero rate of change. It's not going up or down. So in 2000, the rate of change at a certain time was 0. Okay? Now part B is asking the debt per capita was almost constant. We want to say is this statement true or false. The debt per capita was almost constant up to the mid-1970s, and then rose at an almost unconstant rate from mid-1970s to mid-1980s. Okay, so if it's constant, it's pretty much flat. If it's not constant, then then it's going to not be a straight line. It's going to curve at some point. Okay. So if we look what's going on over here, from the mid-1950s through the 70s, the line doesn't change very much. So the rate of change over here, it's a constant rate of change. It might even be almost a zero rate of change. Then over here, it starts curving up pretty quickly. All right. It still looks fairly constant. It's definitely increased, but the rate of trade is starting to curve up. Right. So both of those statements are pretty true. And again over here, let me see if I can maybe draw that a little bit better. So the picture is not wonderful, but if we look over here, maybe if I draw a little exaggerated, from the 1950s to the 1970s, the graph looks like this more or less. It's actually even flatter, it's close to zero, but that's a straight line, that's a constant rate of change. Then all of a sudden, a little bit after 1970, now this is I'm exaggerating what the graph looks like to get the point across. It starts going up like this for a little bit. And then it starts constant again, straight. That does not exactly look like the graph there. I exaggerated the curves and stuff. But can you see over here how that's not a constant rate of change because it's not a straight line at that segment? From 1950 to 1970, it was pretty straight. But then all of a sudden, it starts to curve up. So that means that if we draw tangent lines, the tangent lines are going to be different depending on what point we choose in that segment. Where over here, pretty much any tangent line is going to just be that black line. Okay? Okay. So I hope that clarified it. Now this is the last thing in section 1.2, and we're going to start next in 1.3. I'll just finish this example. Find the slope of the tangent line to the graph y equals x squared at this point over here. Now the solution for this is we're going to get into more detail in the next section. So this is kind of an introduction, so you're not going to understand everything in the example. We're going to give you a piece of information. All right? Now, the piece of information that we're going to give you in this example is that the equation, if we have the function y equals x squared, the slope of the tangent line is given by the formula 2x. So if I tell you what x is, if you tell me what x you want, I can tell you the slope of this curve at that point. So if x equals 1, then the slope is going to be given by the formula 2x. Well, 2 times 1 is 2. If x equals 2, then the slope is going to be 4. If x equals 3, then x is going to be 6. If x equals 10, the slope is going to be 20. So we have an increasing rate of change. We have an acceleration here. And let me see if I have enough time to finish this example. I have 4 minutes. I'm going to give it a shot. Probably not. And this is the very end of 1-2, so we start 1-3 next time. So, okay. So we have the equation y equals x squared. Okay. And we want to know how fast it's changing, say, at the point when x is equal to 2. Okay? Well, if x equals 2, what does y equal? If x equals 2, y equals 2 squared, so y equals 4. So I have a point, which is going to be the point 2 comma 4. Now I'm telling you that my slope, m of x, for this function is given by the equation m of x equals 2x. So if the function is y equals x squared, the slope is given by 2x. So if x is equal to 2, what is the slope going to be? It's going to be, if x is 2, what is my slope? 4. Because all I'm doing is saying, well, if x is 2, and this tells me what the slope is when x is 2, which is 2 times x, so this is also going to be 4. So I know what my slope is, and I have a point on the tangent line, so I'm going to use my point-slope form. So I'm going to have y minus y1 is equal to m times x minus x1. Well, y is going to be, I have a point here, which is 4 and 2. I have a slope, which is 4. So I'm just going to be y minus 4 is equal to, my slope is 4, times x minus 2. So the equation for the tangent line, and this is what we're going to spend the next chapter talking a lot about, in point-slope form is going to be y minus 4 is equal to 4 times x minus 2. And the slope of the curve at that point is just the slope of the tangent line, which is 4. Okay? Now that's all I have time for today. I'm going to post this lecture on YouTube if you want to watch it again. I'll send out an email for that later. I also have your results from the pre-test. I'm going to post those later tonight, and I'll send out an email with information about that too. And have a good evening.